François, let's go.
Okay. Well, I'm very pleased to introduce the next speaker, Professor Holger Karl, who is a professor of computer networking at the University of Paderborn in Germany. We are very glad to have him on the scientific committee. So before being in Paderborn, he was in Berlin at Humboldt University and at the TU, working in the group of Professor Adam Wollisch. He's a specialist of wireless networking. Broadly speaking, he has a very large set of interests ranging from wireless sensor networks, a topic on which he wrote a very influential book discussing both the protocols and architectures. But his interests are, as I said, quite broad. He worked on power control. He worked on various topics that go, in a sense, beyond wireless, in information-centric networking, in cloud computing, in software-defined networks. And lately, he got quite active in machine learning, and this talk today will bear on this topic. Please.
François, thanks for the introduction. That book is actually a long time ago. It's probably no longer even true. So indeed, interests have shifted a little bit. And recently we've done more network management, orchestration type of work. Machine learning has been a tool that we have looked at to apply to these problems here. I would never claim of myself being a network machine learning researcher. I'm just trying to understand what these people do and apply it then to networking. At the core, at the bottom of my heart, I am a networking person. So the work I'm talking about here is together with two PhD students, Haitam and Stefan, and one postdoc, Arun Ramaswamy. He's actually the machine learning person in that gang of four here. And as François already mentioned that currently I'm at Paderborn University, and that's true, but that's only true for a couple more days. So July 1st, next week, I'll move to another place, to the Hasso-Plattner Institute at Potsdam. And I'm taking the liberty of throwing that in here because that means I have a couple open positions. So if you are in the market for a PhD or a postdoc position, I'd very much appreciate to learn from you and to hear from you if what I'm talking about here is of interest to you. I can only advertise Paderborn with the warmest regards. This is really a great city. It's a World UNESCO Heritage Site, cultural heritage site. So it's a great livable place. It's just outside of Berlin. So by all means, give it a look, check it out if you're interested. So, okay, close advertisement part here. Let's get down to business. If I'm not making sense, if I'm making statements that you disagree with, that you have questions, please immediately interrupt me. Please let me know. I probably will not catch it if you type in anything in the chat. So just speak up and just mention things, right? So with that being said, yes, broad research area, guilty as charged. Broad topics of interest. Last couple, 5, 6, 7 years, probably were focused around what has been called this network softwarization. The idea that, hey, the cloud computing guys have been so successful using commodity hardware and just plugging software on top of that. This is wonderful. Let's do the same thing in network. Yeah, certainly. And that branches out into other areas. This certainly relates to data centers. This relates to how you run mobile networks in the sense of a mobile network like a 4G, 5G, 6G, XG, whatever your current favorite number is. And it also has interesting applications really to wireless networks at the core. And I'm going to talk mostly about the network softwarization here. Time permitting, my guess is it won't, but time permitting, I'll try to say a couple of words on what we are playing with in the wireless networks context, machine learning in a wireless networks context here. So when we discussed the pitch of the talk here together with the Links colleagues, we thought going high, going low, going in detail, going high level, and I'll probably do neither. So I'll go sort of in the middle and try to give you a gist of it, but still provide enough teaser information to make sense. That also being said, I'm probably going to repeat a couple of things I said in my inaugural talk a couple of months ago. So please bear with me if I'm repeating myself here. Now, let's get into the network softwareization part here. The typical association people seem to have when this buzzword comes up is something like this, right? You have your network where you have services, you have your firewalls, you have your load balancers, and then outside of the network, you are talking to servers, which do whatever the user actually wants to have done, right? That's sort of probably the first association and impression people have. And there's nothing wrong with that. You have your individual functions, you plug them together in the sense of a chain or possibly a general graph. If you've got branches and mergers together, this gets a bit more interesting than a linear chain. And that's fine, right? And this is also nice in the sense that most of these network functions often are stateless, so you don't need to worry so much when you want to scale in, scale out, when you want to move flows between different instances of these functions. That's all great. But then think back to what Jim Carosi yesterday talked about, right? This network as such is all great, but we need to look at applications. We need to climb up the stack to make things viable, interesting, maybe also even commercially viable. And I agree with that. So in addition to this mere network function virtualization, we also need to look at the applications. And if you then talk to the software engineering folks, they say it's exactly the same thing. The picture in software engineering looks exactly the same thing. It's no longer the big monolithic piece of software sitting on a server. There also, you got your software broken down into individual pieces, which provide individual tiny little functionality, like a web server, an application server, a database, and then the terminology is a little bit different, granted. Yes, they talk about microservices and chaining microservices together. But, you know, at the end of the day, potato, potato, these figures look very much alike to me, right? Yeah, there's differences. Maybe you've got return traffic, maybe you don't have return traffic going through your individual functions, but high level boxes, functions, traffic going through, you need to deal with that, right? And you got users sitting somewhere requesting that. So if you subscribe to that notion, if this is true, then we can ignore all these differences and look at a slightly more abstract picture, right? So what I'm looking at is I have a service of whatever type, being low-level network functionality, being high-level application, described as a graph of whatever type of individual functions and a user making requests to that. And this here is now a unidirectional example. The previous slides had arrows going back and forth, so they're bidirectional, minor detail, right? So I got this. And I also got infrastructure, right? At the end of the day, I need something to run my functions on. I need something where I can execute software. There's no getting around it with all the virtualization in the world. At the end of the day, I need an infrastructure. So I got routers, I got data centers, and again, call it what you like. It could be the data center outside of the network, high capacity, very good economy of scale, gorgeous for big bulk applications. Or you have the edge, the fog type of application scenarios where you have your infrastructure at the edge of the network, but sort of at the other side of the edge, close to the user, right? So how do I get from this to that? How do I map my abstract function view of a service onto a concrete view where I can talk about instance executing code dealing with a particular request of a particular user? Now, this is what is often called the management and orchestration problem, if I'm subscribing to the ETSI terminology here, commonly abbreviated as the MANO problem. And there's lots and lots of sub-problems here, right? MANO really is just a battle flag here, not a specific problem. So a typical sub-problem here would be placement. Where do I place a particular instance of a particular function? So if my user is sitting here, am I mapping this abstract instance of A onto this concrete cloud router, base station, whatever, and B and C and D go over here, right? So the placement problem. What happens if additional, latency, and why am I doing that? Why am I not putting everything towards the edge in a big data center? Of course, latency, right? This could be dealing with all these requests here. So if I'm running that at the edge, I'm getting the advantage of lower latency towards my user, obviously so. Now, that's great. What happens if additional users come in, right? My user population changes, making requests now maybe from somewhere else. Of course, user shows up here, wants to use the same service. I can route the traffic over here, processes it over here, but there goes my latency advantage, right? This nullifies, this voids all the benefits I had from this complication if I have to carry all that traffic over here. So instead, I'm scaling this out by installing, by bringing up a new instance of A over here, closer to my additional user here again, and then stitching this back together by using B and D again to serve this additional instance of A. Scaling, how many? So how many, where? These are the typical problems. How do I route between them? How do I schedule order sequences of these requests when they are competing on an individual instance? All subtypes of the manner problem. And all of them are nice and typically NP-hard problems, but the challenge is I need to do this very fast, right? I usually don't have much time to stretch my head and come up with complex solutions for these problems. 5G statement at one point was to say that the deployment of a new service should be done within 1 minute, which is considerably shorter than the days and weeks, what you see today in operational networks. But if this is over the top services, application services, even 1 minute might be way too long, right? So I don't have the luxury to do complicated things here. Why would I do complicated things here? Well, the problem is complex. It is, has many aspects of many different application optimization problems. You find hidden inside things like a facility location problem, multi-commodity flow problems, all of them typically, as I said, NP-hard. And sure, you can write your optimization formulations. You end up with your mixed integer linear problems. Many variants are quadratic, so none of that is really nice, right? Okay, then you go to approximations, you do heuristics, sure, or you look at machine learning. So last time in my last talk, I talked more about the heuristic approaches for that, possible approximations. Today, I'd like to talk more about these machine learning approaches for these type of problems, okay? So to pick one example, now let's get a little bit more concrete. Let's reduce the flight level a little. So existing work, for example, lots of papers take a long-term perspective of that problem, saying, okay, I know something about my aggregated traffic statistics. I know about where my users typically come from. I can smooth out, I can average over long time horizons. I have good predictions for future traffic. And then life is nice, right? Then you can do interesting optimizations to prepare yourself for that. Maybe I don't have that luxury. Maybe I need to react very quickly to online requests showing up rapidly, user flows coming in, user flows disappearing, and I need to track that very quickly. So that does not sit well with these types of approaches. Maybe I can get all the nice results out of my approximation ratios, all my good heuristics. Maybe I can only get that by making rather specific assumptions about the scenarios I look at. For example, typical proof technique for an approximation ratio, you assume something about the structure of the services. They are linear chains, they are binary trees, and then great, then you can do interesting things. Maybe you don't have that knowledge. Maybe you don't have the luxury of dealing with such type of services. So maybe things change. So I'd like to have something that self-adapts to new scenarios, new type of services that I haven't seen before, changes in my infrastructure. I don't want to rely on inbuilt, pre-specified knowledge of that type. And knowledge should not be global, right? And it should certainly not be a priori given. So I want to deal with or rest only on partial knowledge, things that I can plausibly, realistically actually observe. I need to be able to deal with delays, with incorrect observations, all the reality kicks in type aspects that you see here. Okay, so if I want to do all that, can I come up with a plausible solution? Hopefully, this is where all these deep reinforcement learning work then should shine. So we try to put that into place by doing such a self-learning coordination approach for these type of scenarios. Okay, so what can we plausibly learn? I'm not explaining reinforcement learning, etc. We had yesterday good tutorials on that, so I'm assuming that this is all known. So my scenario looks something like that, right? I have my individual sites, base station, clouds, doesn't matter, links in between. I have my user population distributed at the edge of my network, making requests, right? And maybe I have a service here, the beige version of my service here, where I have a component 1 and a component 2, doesn't matter what they are doing. And I somehow have a distribution of these components there, right? Okay, plausible, maybe. So what I'm then going to do, I'm going to have my agent sitting outside of my network, making observation, monitoring what's going on. It's going to update rules and it's going to get rewards, whether these updated rules were good or bad. So far, so trivial. The rub is, how do these rules look like? What am I actually updating there? Now, I could do something where I specify very much in detail this component sits on that particular site, dealing with user traffic coming from this base station, etc., etc. Right? This is certainly part of that perspective, and there are papers who do exactly that. I'd like to do with less. I'd like to do with as little as possible here. And here in this first part, we're actually doing with still quite a lot, but let's try to shrink this down to what we can get away with. So how about the following idea? What I'm actually only going to learn as rules are local rules that tell a node how to deal with demand for a particular service, more specifically for a particular component of a particular service, once it arrives at a particular node. I'll make that clearer on the next slide. So my idea is I only want to learn outside of the network. I only want to learn local rules that I can fully apply and fully deal with locally, right? And then I'm distributing these rules in the sense of a table that expresses all that I actually going to need there. So how does this table look like? What am I going to put in there? That table here tells me, if I'm looking at this node V1 here, that tells me, look here, we have a service S1. That service S1 has two components, C1 and C2. And the request for such a service, a user request coming in, either still needs to be processed by component 1, firewall, or it might already have traversed component 1 and now needs to be processed by component 2, web server, load balancer, whatever, right? How do I know that? Well, if you think of things like network service header, you know how far in the processing stage of such a service chain you are. So this is knowledge that is part of your packet. You can just look at the packet and you know that. Okay, fair enough, I know that. And then I'm doing something very, very brutal. Brutally simplistic in the sense, I'm going to specify for all nodes in the network, I know, yeah, bear with me, for all nodes in the network, I'm going to specify what's the probability that if a request for service 1, component 1 arrives at this node V1, I'm going to process it at V1 or forward it to V2 or forward to V3 or forward to V4, etc., etc., right? This table is all I'm going to need. This table implies, or from that table I can extract scaling, how many components are there. I can, it implicitly encodes forwarding, it implicitly encodes placement, right? Where is something happening with, okay? So can I learn these tables? Can I learn these tables for node V1, V2, V3, V4, etc., etc.? Okay, so can I learn these stochastic flow rules? Okay, if I want to learn that, what can I plausibly observe about my network? Well, as I said, we are in the scenario where I'm learning outside of the network. So anything I can observe should not be too detailed. It should be reasonably aggregated so I can deal with delays. And I don't want to learn too much, right? I don't want to observe too much. So is it plausible, for example, to say I know the utilization, an averaged, smooth, time-averaged utilization of a particular node? I would think so. Typical monitoring system can do that. Can I deal with link utilization? Probably. Can I deal with what else is going on in my network? Probably. So let's make this a bit more concrete. My observations, what I want to know from the network is actually very small. I want to know the utilization of each node, average of all services, average of all components, right? I don't care what the individual components do. And I want to know where load arrives. At which node is which service requested with which rate, right? And that's it. That's all I want to observe, okay? Plausible, I think so. It's smooth, it's average, so I guess I can observe that. What are my actions? My actions is exactly this. It's exactly this table, right? I want to learn these tables and then distribute them. So my actions are this table for every node, for every service, for every component inside that service, and for every other node in the network, compute the probability. Okay? Possibly huge, right? This is quadratic in the number of nodes in the network, clearly a scalability problem, but bear with me, we'll get this smaller. Okay? It's continuous, so yeah, maybe not so nice. We need to deal with the continuous aspect here, but that's all doable, right? And as reward, again, typical reinforcement learning stuff, I can do whatever I like, more or less. What I'll start with, for the sake of argument here, I'll start with the number of flows that are successful, that I can actually deal with. I'll introduce a delay bound in a second, so I don't want flows circling at the network, searching for the processing side at some point. So I have a delay bound later on. And the actual delay that I actually see, small end-to-end delay, is certainly something that's nice. Okay? So let me skip over all the details here. So the characteristic here is the continuous action space that I have here. So something like a DDPG learning approach seems suitable. This worked out nicely. And again, to emphasize, we have offline training and we have online inference, where the online inference just computes these scheduling tables. Okay. To speed this up a little bit, we tried that with different network topologies, the typical topology zoo thing. We varied stochastic arrival patterns. We compared that against heuristics, fancy heuristics, as well as straightforward heuristics. And look, I wouldn't be talking about this if the reinforcement learning scheme did not outperform. Yes,
could I ask a small question, just to understand? Since you asked us to interrupt. So
by all means, please.
If there were reasons, right? So I was wondering, so you allude to the MDP, right? And so you are in this, and so what you want is to learn the parameters of the MDP, and that's where the learning will be, right? So if you would know that, you would just apply an MDP, which would be a sort of centralized MDP, which is the view of the operator running and telling where to load this or that flow,
these
right?
Tables, yeah.
Right. But you don't know that, and then you have to, in this centralized view, you have at the same time to do the placement and to learn this table, and that's where really the core of the problem is. Is my understanding?
Yeah,
okay, thank you.
Exactly. And I actually do not explicitly learn placement because this is implicitly encoded in here. Anytime I have a non-zero here, that means I need to place a component on that particular node, right?
Yes. And it's an MDP and not a game, because the operator is deciding what to do, and it's not the applications which are competing to find the best spot, right?
Exactly.
Okay.
Yeah.
Thank you.
Yeah, exactly.
Sorry for the interruption.
No, please, by all means. That's why it's not pre-recorded, right? So again, time flies, so let me skip over the details here. So we looked at different arrival patterns, MMPPs, we looked at real-world traffic traces, we varied things like the number of ingress nodes where this works out. And look, I wouldn't be talking about that if the DRL would not outperform the other schemes. So that's nice in the sense here of successful flows. And the obvious downside also is really long training times. So the one node, the largest network we looked at with 53 nodes, it needed something like 1,400 episodes. Well, it did reasonable after 200 episodes. We are sort of conjecturing that there's still traffic going up with 20,000 time steps per episode. So this is actually substantial training overhead that was necessary to get there. So am I happy with this? Not really. I mean, the obvious downside of this scheme here is the quadratic size of my learning problem, quadratic in the number of nodes. I mean, am I kidding you, right? Almost, right? So this can't be the end of the story, and it surely isn't. So as I said, let me skip over a couple of things here. Let me do an intermediate summary. So far, decentralized learning kind of works. It's actually outperforming typical heuristics. These distributed flow tables seem a good idea. They encode a lot of things in a very elegant fashion, but the size is just too big. So I need to cut this down. So can I get this done more? Can I distribute some of that? So my essential reinforcement learning approach had the RL agent for the entire network, one agent for the entire network, quadratic size, right? That was not so nice. Can I get away with a scheme where I just need one agent per network node rather than for my entire network? I still get good results. Can I get away with global observations and just do local observations? Can I get away with this? Basically, I'm doing central inference here and do distributed inference. Everything's spread out, right? So high-level picture would be centralized training. I had my different environments. I observed everything. Maybe I ran parallel agents to speed up the learning process, but that's beside the point. So I had this one agent here that then distributed these scheduling tables down toward my individual nodes. Alternative idea, I'm still training in a centralized fashion, but I'm now distributing these much smaller agents down to my individual nodes, not the scheduling tables, they sort of emerge. I'm distributing down these agents to my individual nodes, and these agents, the observation space should be much, much smaller, right? So that's the idea behind this. So maybe a little bit more details on that. So once I see flow arrivals, there is again the MDP behind that. I can have basically the same observations I had before, right? I can look at my flow, how far in my service chain am I, how much time do I have until a deadline for that flow expires, link utilization, node utilization, all easy to locally observe, right? No problem. The one thing that's a bit fishy, I admit, is I want to know delays to egress nodes. We need that to shape rewards a little bit. Otherwise, this doesn't really converge, right? And then I'm doing something even simpler than before. When I before had this scheduling table, basically here I'm just saying this local agent for this input has one action, a discrete action now, that says, okay, do I process this thing locally, or do I forward this to the eighth neighbor? Okay, why is that weird? This is weird because now I'm saying I have exactly the same agent, not having knowledge of an absolute node identifier, nor of absolute neighboring identifiers. I'm just numbering my neighbors, 1, 2, 3, 4, 5, right? And I'm using the same agent on all nodes. This is actually, I find this totally extremely counterintuitive, and it still works. There's still enough structure inside that so that you still can get plausible behavior out of that. The idea would be you need to look at your rewards. Well, you get, not surprising, right? You give big rewards if a flow completes its service chain successfully within the deadline bound. You give a big penalty if you drop the flow. And as I said, we need to do a little reward shaping to steer the flows towards the egress where they want to leave the network. So there we do a little reward shaping. Very, very small rewards between 0 and 1, for each progress you made towards that. That was necessary to get this thing to work. Okay, and let me emphasize that again. This works without knowing node ID, without knowing absolute information. This is this node, these are that neighbors. There's enough structure inside these observations to deal with it's the fifth neighbor. Go to the fifth neighbor under these circumstances. Personally, I didn't believe it when I first saw that. It works out. So as time flies, yeah, you get better successful slopes. The interesting thing is you even outperform the central learning approach, caveat, with the same amount of training, right? Because the distributed version learns so much faster that at comparing for equal training overhead, you outperform the central case handily, easily. Right, it nicely generalizes when you vary things like ingress nodes, you throw traffic at it that it has never seen, it still generalizes to that. Okay, how are we doing in time? I think we're doing terrible in time. Yeah, we need to leave a little bit more time for questions.
Yes, you have about 10 more, 15 more minutes, but if we want to include time for questions.
We want to have a couple of questions, I guess, yeah.
10 more minutes then.
Yeah, so let me skip some of these results. You know how you write papers, right? You have glorious results in the end, of course. So let me summarize this aspect here. Let me try to summarize that here. So what we set out to do, we wanted to get away with the need to custom design specific heuristics, specific approximation problems under a lot of additional assumptions and work with realistically available information and see how far we get, right? And then see how far we can self-adapt, generalize, etc. And it actually works out reasonably well. We saw that this is robust to sudden changes. We could throw unforeseen traffic arrivals at our agents and they still worked out nicely. It can adapt when we fiddled around with changing the target, so emphasizing delay more, emphasizing success ratio more, and it still handles that in a plausible fashion. And the distributed version actually works nicely if you just have local fine-grained per flow control, then it gives you such robustness and scalable network management without that. If you want to play around with that, all of that is open source. The centralized version probably has a better name, deep code. The distributed version just is called distributed DL coding. Still need a better name for that. And that's all I basically wanted to say here for this softwareization part. Let me just maybe spend 2 minutes, give a little teaser on the wireless networks. I think the application scenario is quite cute. So I'd like to talk about that a little bit. Imagine you have a lecture hall, meeting room, whatever, right? Conference hall, something like that. And you have multiple speakers, which might move around, which might take turns, etc., etc. And we want to record that, right? And a typical scenario might be you have microphones sitting at the ceiling, which can then act as a distributed microphone array and record and do echo cancellation and speaker separation and all the fancy things you can do with microphone arrays. And let's throw in the additional ability to move these microphones, right? Now, okay, if I have fast moving microphones, if they are moving at instant speed, at infinite speed, then I put all my microphones to the speaker, and when the next speaker starts, I whoop, move them over to the next one, and I have perfect things. Well, not so fast. First, not so fast in the sense they don't move at infinite speed. If you don't want really, really complex scenarios where, you know, wires suspending your microphones, if you want to have something, I don't know, crawling on the ceiling type of things, they are not going to be fast. And depending on your application, depending on the acoustic signaling processing application, you want very different behavior. In some scenarios, you want actually all your microphones clustered around the speaker. In some of them, you want some clustered, some far away. If you want to do echo cancellation, for example, you need some far away. Depends what you want to do. So it really depends, right? It really depends what your application is, how the best scenario should look like. And well, of course, sound at the microphone doesn't help you. Let's say we have an additional access point where we want to offload our recorded data to. So I'm faced with the decision problem to say that which microphone moves where, records which speaker, transmits when to an access point, right? And now just turning on more microphones is not necessarily a good idea, right? Because then my wireless medium gets overloaded, my delay goes up in the wireless medium. Even though my acoustic utility might be better, my network is not necessarily able to keep up with that. So I have contradicting aspects here. So for example, just to again make that a bit more concrete, network quality is probably easy to imagine. I need a certain time delta to deliver data from my microphone to the access point as an R-based, contention-based, whatever, right? And you have acoustic gains. And here, this is way outside our expertise. We cooperate with our colleagues from acoustic signal processing here. There, it depends on certain threshold distances, on the acoustic model you have underneath. This is actually very simplified already, where I'm saying I get a certain gain from a microphone M for a certain distance. And then it's sometimes the third root or the power to the 3, similar to what you see in threshold distances for wireless. But a factor of an exponent of 3 and 1/3 is maybe not what you typically see in wireless, right? And then, okay, we bunched that together as a typical weighted sum. Again, it's not so surprising. And then we looked at what can we learn? Can we learn ideal movement patterns compared to heuristic? And maybe just here a little video for that. The red is the active speaker, the gray is the non-active speaker, black is my access point, and the green dots are the other microphones. And yeah, they are kind of learning something, but not really. It actually works better in the pick best case when I want to have just one microphone close by, rather than multiple of them. Then this works out better. And comparing to heuristics, this kind of works, but not so well. So that would need more details here. Let me try to wrap up. So this idea that I want to distribute services, let me circle back to the beginning. So I started saying that my services are composed of individual components in a chain, in a graph, in whatever, right? Both on network as well as on application level for all types of different scenarios. This trend that service execution is there, I'm pretty sure this will stay for the foreseeable future. It appears in so many different scenarios. It has so many benefits. So we need to deal with that. And the challenge for the foreseeable future is that this will be here to stay, but our infrastructure is no longer as nicely defined as it used to be. It's not the network that is stable and unchanging and eternal. It's also not a data center where, yeah, sure, once in a while a server fails. But if you think of your vehicular network scenarios, this becomes much more volatile, much more heterogeneous, and I don't think we have the tools at hand yet to deal with that at scale, at the required speeds, at the required trust levels, at the required business models that appear when you start trading resources versus you delegate trust or you delegate responsibility for executions in a volatile environment. None of that is really there. So a long-term challenge I see for that is to manage service instances in this stated sense over a volatile infrastructure. And with that, I think I'll stop, and I'm happy to take questions for whatever time remains. Sorry for keeping talking.
Thank you very much. Okay, thank you so much to be for this very nice lecture. So, questions. So I have a couple of questions. The first one is a terminology question. So, I mean, these problems have connections with the placement of tasks in multiprocessing, parallel computing. I mean, and so what? So why is it called orchestration and what type of algorithms which were used in parallel processing of the multi-programming with flows of tasks? What part of that could be used if you would not use machine learning type ideas?
So why that is called orchestration? Oh, that is, I'm not sure I can answer that. I think this is because the ETSI working group that came up with that might not have been aware of the other field and came up with a new term. I don't know. I'm speculating. I would not want to do that. But you're perfectly right. These are problems that are known from parallel processing, also from, what was it called? When you distribute parallel jobs over multiple compute sites in HPC. Forgot the term. You know what I mean. The natural problem at the core is network embedding, right? You have your infrastructure graph, you have your application graph, and you want to embed that. And that's sort of the core of that. And from then you start thinking, well, yeah, maybe a difference is that you have incoming requests, which is not typically the case in HPC. Depends, you often know where your data is in an HPC scenario. So this is less volatile. This does not change so much. And here, what you actually do have is the ability to scale to scale out, which in an HPC application is also probably not so typical. A VNE in a virtual network embedding algorithm in its core form usually would not think about scaling out. Right? You have your fixed graph and you have your fixed underlying infrastructure and you look for the mapping and that's it, right? So the ability to rewrite the graph that you want to embed, this is something not usually seen in the parallel computing community. So that is usually how I explain that in class, in a lecture when I'm trying to get this point across.
Okay, yes, thank you. Yes, and so I mean, I will try my other question unless somebody interrupts me.
We have a question.
We have some questions.
Oh, good. Let's go on and go for my questions later. So please.
Yeah. Okay. Yeah. For the embedding problem, it seemed it was implicit in your reinforcement learning formulation. Because when there was a non-zero entry in the table, it means there you have to have a virtual node embedded. If I
exactly. Yeah.
But this implicitly means that it costs nothing to put a virtual node there. And so then, if the requests are not stationary, so you have to possibly change these nodes, migrate. This cannot be captured by the model. So, what are the modifications that would be needed to handle this?
Yeah, excellent point. Keen observation. Indeed, this model, in the way I explained it, makes exactly that assumption that it's a zero cost in both in time as well as in transport overhead to get the executing artifact to wherever it is needed, right? Virtual machine image, whatever, right? Doesn't matter. And that is clearly wrong, right? This is clearly not realistic. That's exactly what I'm currently writing the proposal for, to find the, to deal with, to incorporate that also. This is surprisingly under-investigated, to incorporate the need to actually provide the piece of software where it is needed, right? This does have overhead. And then you need to think of startup cost, possible standby. You want to, in a volatile environment, you want things to be dependable. So you probably want to run a hot, warm, whatever type of standby. That also causes cost, right? This is also, there is a little bit of work there, but this is not really investigated. But yeah, I totally agree. Keen observation. This is something I swept under the rug here. I think we're already 5 minutes over time, if I'm not mistaken.
Oh, we started late. We started quite late. So I mean, the questions are important. So let's go on for a few minutes, unless Sébastien tells us not to do so.
It's my internal German that says be on time, right?
Yeah. You're partly in Paris.
We're sitting here in Paris and everything is late, so don't not being direct.
More questions. More questions.
The coffee break, so it's okay.
Jean, you had a question.
Yeah. So enjoyed the talk very much, Holger. Thank you. I wanted to ask a question about you have a worldview where it's one big network and everything happens in this one big network. And in real life, at least with the current, set of industry players, the network might be separate from the network operator might be separate from the data center operator where I need a computation done. If you think about IoT environments, there's lots of different holders of data that I may need to interact with in order to do something. And so I'm wondering whether whether you think the centralized model that you have where everything is all in one entity will give way to a more distributed view and federated learning sort of being the more natural approach for doing the optimization rather than sort of a one big center.
Absolutely. Centralized views are just bogeymans here, right? This is what you can use to scare people with because they are so absurdly unrealistic. That being said, the idea to divide that into hierarchical approaches, into federated, coordinated, collaborating approaches, these ideas clearly exist, clearly are around. The interesting question is, what is sort of the level of hierarchies? What are the boundaries? Sometimes these boundaries are quite natural. Say you have France Telecom. Then you could entertain the idea that, okay, France Telecom's network is France Telecom's network, and this may still be small enough so that it's amenable to a semi-centralized perspective, right? Let's pretend for the sake of argument, right? But then, as you point out, what's with Google at the outside? What is with the IoT stuff? Where are the negotiation APIs? How do you delegate responsibility? It's relatively easy to say that, okay, I give you this request and you execute it, right? There's been plenty of projects on that. But what happens if that fails? Who pays damages to whom? How is this handled? How is this policed? Then life gets much more complicated there. I think this is much less a learning or algorithm design or even system architecture problem. This turns into a business model problem.
Right, and in a business model, all of that data is absolutely hidden from the outside, right? And so in your function graph model, again, it seems to me that where I place things, it's not so much, oh, I give you something and you give me an answer, but it's how fast you give me, and then that's going to impact how, which of my instances that are under my control where I want to do that, where I want to actually execute something. So somehow it's distribution, not so much because it's too big a problem, but rather that you've just got these different players and these players are going to hide information from each other. But how you stitch those together in your function graph will depend, that's what you need to learn in sort of that federated environment.
I agree, yeah. Also, what if players are not truthful?
Well, yeah.
Perhaps there was a short question, which is a math question. So in these MDPs, when you learn the structure of the sort of part of the problem, I mean, there are conditions for this to converge. If I remember well, the nice book by Vivek Borkar and Ari Postatis. So so I mean, do these conditions play a role in the theories that you develop, or how do they spell out in these special cases?
Oh, that's a very broad question. The one thing to think about is, for example, these cooling sequences, how quickly you reduce your time steps for the learning steps. I don't think we can squeeze that for all the different problems inside. So far, what we looked at, we think we're not the machine learning theory guys, but we think that yeah, this should converge from the best of our understanding here. So I admit I'm punting here, but that really needs a longer discussion.
Mm-hmm. Thank you. Okay. Any further questions before eating all the whole break?
Bonsoir.
Yes.
Yeah, we have a problem with the micro. It's getting off by itself. Getting mute. Holger, very nice talk. Thank you very much. This is Daniel asking. In the same area, I would say that the question, you may also have one infrastructure, but which is open, enabling third parties to add functionality. This is something that is becoming possible with the ORAN and all these type of new architecture that are being specified. So how do you see these things working if you have this possibility of having different players being able to add functionalities over a part of this infrastructure to orchestrate specific services for them?
I'm afraid I'm not sure I totally understood that. So I think what you said is, correct me if I misunderstood, what happens if I have third parties bringing in additional functionalities? So are you talking about functionalities as in new services? No problem, that's what this is intended for, right? I think what you meant is third parties bringing in orchestration functionality. Is that what you were saying?
Exactly. I mean,
okay.
The possibility to orchestrate them to provide new services.
Yeah. So let me try to make this a bit more specific to an example. Suppose you have a service that you want to scale out, and scaling out is trivial for a service that is stateless. But what if your service is stateful? Then maybe there are situations where your service cannot be scaled out because it's in an inconsistent state, because it's just inconvenient to copy all the necessary state, etc., etc. A general purpose orchestrator probably cannot know that. You can think of writing complex description formats, but I have no idea how that would work out. So one idea is indeed to say that forget this general purpose orchestration. This will never work anyway. We need something that is specific to each individual service and understands what this service does, right? And then knows how to orchestrate, how to scale, place, blah, 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 whatever. I totally agree with that. I think that makes a lot of sense. The question then becomes, how do you deal with conflicts? Right? Then your service one says, yeah, I want all the resources, and service two says, I want all the resources as well, right? And then how do you deal with conflict saying that, okay, you want some sort of fair allocation of resources? What is fair here? What type of fairness model do you want? Who is paying how much? A couple of people played around with that, but I'm still lacking the convincing answer for that. But yeah, I agree. That's an interesting point.
One of the things we are looking at, together with Andrea, by the way, is one of the issues we have today is that everyone is talking about mobile or multi-access edge computing, but the carriers, the telcos are not really investing on that because they're very busy doing many other things. So we could imagine that the service providers, those that need this infrastructure, like the transport infrastructures or the energy infrastructures or whatever, will somehow co-invest on this and have smart ways to share these resources. And if you do so, you need a smart way to decide how to allocate those resources, and you need somehow to coordinate the orchestrators of each of these players, right? So this is the type of things we are interested on, and it seems quite connected to what we're doing.
Yeah, I totally agree. Probably possible to deal with different pricing models to say that, okay, if I'm Google, I'm co-investing, so my services are allowed to run cheaply on my co-invested infrastructure. The other guys, it gets really expensive. Plenty of ways to think about that. I agree.
We're using some game theory to model these issues. So we will be, I guess, Andrea, if joining me on this, we will be very glad to keep talking.
Yeah, I'd be happy to, absolutely. I think, if you look at the time.
We give the floor back to Sebastian, who decides. Thank you so much for the very very nice and lively talk. Thanks a lot.
Thanks for your questions, much appreciated.
Thank you very much.